As was already stated, my name is Rastислava. Regarding the questions, I would actually suggest to wait for the first part of the talk that will be finished, and then we can, if there are some uncertainties to be asked, and then the second part. This is the outline of my talk. Well, in principle, my talk is devoted to two major parts. The first one is the theoretical treatment of single and double beta decays and theoretical calculations. And then the experimental studies with Baikal GVD neutrino telescope. So that practically means that I would like to first conclude with the first part, then I will give you opportunity to ask me some questions if there will be some. And we will proceed with the experimental studies. So in the beginning, I would like to give you something like the brief introduction, the common one, to neutrino physics in general. Like in the beginning of the 20th century, there was this commonly known issue of the continuous beta spectrum, energy spectrum of electrons in beta decays. That was not clear by that time. Why is it continuous as far as the nucleus is decaying into the daughter nucleus, and there is an electron emitted by the energy law of conservation? You would expect discrete spectrum, not the continuous one. Well, one of the wrong explanation that was paraphrased is that by Niels Bohr, that energy might not be conserved in the beta decay, which later on found out that it's not true. The genuine idea whatsoever in the history of physics was done by Wolfgang Pauli, who proposed that together with electron that is emitted in a beta decay, there is also some additional particle that we cannot see. And it was quoted that he has done the most terrible thing, inventing a particle that cannot be detected by that time. So this was actually by these famous letters sent to Tübingen, which is a picture that I made there up on the Churchill. And I need to quote that the last year that we would be in a standard situation, we would be celebrating 19 years of neutrino physics. But due to the pandemic and COVID situation, I was not able to quote this at any conference. That's why I'm taking the privilege of this laboratory seminar, at least. So he actually proposed the existence of the neutrinos. Nowadays, the picture is slightly different. We know that there are different sources of neutrinos. I would like to just briefly give you this idea that in the first part of the talk, I will be speaking of neutrinos at the MeV scale, mostly connected to nuclear physics reactor neutrinos in beta decays. Later on, I will move to the higher energies, which I will be speaking of in connection with neutrino telescope Baikal GVD. So by proposing this idea that there is another particle that is emitted in the beta decay together with electron, there has been studies to one of the fundamental questions: what is the mass of this particle? Firstly, it was proposed is something like 100 of the mass of the proton, or not more than that. And for years, it is not clear whether it is zero or it wasn't zero. So later, after this proposal, that was another genuine idea by Enrico Fermi, pointed out that by observing the endpoint of the beta spectrum, you should be sensitive by looking close to the endpoint on the effect of the neutrino mass. It simply says nothing else than just you can take the equation I quoted here, tritium decay, that if you have difference between the mass of the initial and final nucleus, extract the electron mass. The only thing that why the electrons cannot reach this value is simply just the effect, it's the kinematical effect of the neutrino mass. And this was performed by Hanna and Pontecorvo, the first experimental measurement with the rough estimation of 1 keV. So this is in principle indeed the genuine idea that since 1934 has been used throughout almost, now we will be reaching almost a century, in studies how to extract the neutrino mass by observing beta decay. I would like to just propose just one thing, that for that particular case, there was a American physicist Franz Neville Curie, I would like to highlight, written with K, not with C, who found out that if you will take the spectrum, beta spectrum, for the LO transitions, simply divided by momentum, energy, and the function that is called Fermi function, taking into account Coulomb effects of the emitted electron with the nucleus, then you will obtain a very nice feature of this function, which is called in his honor Curie function, or sometimes quoted as Curie-Fermi function. And that's the dependence on the neutrino mass. Simply, we have here the fourth root of 1 minus mass of the neutrino divided by the point remaining energy. If you will think of that the mass of the neutrino is 0, then what you will obtain in this function is simply just a straight line. If the neutrino mass is non-zero, there will be some tilt. And immediately you can understand that this is the advantage of constructing such a function. Simply just observing non-linearity of this Curie function tells you whether the mass of the neutrino is 0 or non-zero. By taking into account this fact that was actually other experiments that were observing by this way the endpoint of the beta decays, mostly aimed for the tritium beta decay. Being 2 years ago, I would just be presenting the very famous Mainz and Troix experiment, but recently, Karlsruhe expert Marian Catherine at Karlsruhe Institute of Technology put another more stringent limit on the recent status of the rest mass of the neutrino. So the advantage of this kinematical direct measurement of the neutrino mass from the endpoint spectrum is that actually it is independent of any nuclear physics input. While on the other hand, what is really what is necessary to do is to have the precise description of this theoretical spectrum. And that was something that we will be investigating in taking into account the relativistic approach to this tritium decay, which takes into account nuclear recoil. Because in the common approach, the standard one that I showed you in previous slides, non-relativistic nuclear wave functions were used. Nuclear recoil was usually neglected, stating that the mass of the nucleon is much larger than the mass of the electrons. And then simply you will end up with this phase space factor that you were able to obtain the information on the neutrino mass. Then what we were doing, we were analyzing the tritium beta decay in a relativistic elementary particle physical treatment approach proposed by Primakov in 60s, but not for tritium. And we treated the analogy between the free decay of neutron to proton as the hydrogen decays into a helium. So the unique results that we obtained were actually that the nuclear recoil was reduced by 3.4 electron volts by the standard common formula that you would derive by non-relativistic treatment. And then what we have done is that we show that eventually the same you will obtain from the very complicated formula of the exact electron spectrum, practically the same dependence of the Curie function on the neutrino mass is obtained. I highlighted and quoted the terms that will appear, that they are the most important ones. So this is what has been done by this relativistic approach to tritium decay. Well, further, what I would like to stress is that you don't need to use only tritium, which is actually very fashionable isotope to be measured, but also other isotopes that appeared on the stand, and that is actually 187 radium. That was proposed firstly by the MARE experiment, and they stopped for some time, and I hope that there will be some new fresh wind and they will open the MARE 2 phase. The difference between the tritium decay is that here with the radium beta decay, you are dealing with the first unique forbidden beta transition. That means that the change of the spin and parity between initial and final nucleus is 2 minus. On the other hand, unlike the tritium, the radium does have a relatively very high half-life. So that means that the natural abundance in nature is about 60%. So that is a little bit advantageous, unlike the tritium. Well, and unfortunately, as I said, the fact of the first duty forbidden beta transition requires that the leptons, electron and neutrino, need to be emitted in high partial waves. That means in this particular case in S wave and P wave. What does this tell us? This tells us that the spectrum is not that simple as in the case of the tritium decay or in general in low transitions. So further, the analysis go that way that we wanted to analyze what is eventually the dependence of this spectrum on the neutrino mass, because that's our game. We would like to extract from this beta spectrum also the neutrino rest mass. Now, the electron energy spectrum looks like this as a sum of two contributions. I quoted here in these oval shapes. Now, the first one on the left side in these brackets stands when the electron is emitted in a P3 half state. Subsequently, that means that the neutrino is in S1 half state. So together, they carry out the 2 minus angular spin momentum. Well, the other term in the brackets, here is the plus, it is a coherent sum of two contribution, is when the electron is in the S1 half states and then the neutrino is in the P wave states. That means that, again, the 2 minus is carried out by the lepton pair. In this principle, one may ask, and what is the weight? What is the contribution of these two contributions to the overall decay rate? And simply by numerical analysis, we may show that it is the P wave of the electron electron in the P3 state that is dominant. And as far as you can see by this ratio, it's mostly like practically almost the whole spectrum is governed by the P wave of the electron. So these theoretical findings that we have found numerically by our calculations are in good agreement with experimental measurements that were published a few years before these studies were made. Now, this is what I'm quoting is the shape of the spectrum for the S wave and the P wave, that they are normalized to unity and they look different. But this will be more important on the next slide. I will come back to that one. Now the question stands, what about, now I need to go back one slide, and what about the Fermi functions? During the tritium case, I said that it is a function that takes into account the Coulomb interaction of the emitted electron with the daughter nucleus. Now here we have two different Fermi functions. And that was the reason why I was curious, how can they change this picture of the spectrum? Is there some effect, or perhaps is it just some negligible rescaling? So that was the idea that I will be also using in the next part of the talk in the double beta decay studies, is that what we have made is simply just further analysis. Usually people, what they're using is analytical approximation to these Fermi functions. They just use some gamma functions, confluent hypergeometric functions, and so on. What I took is then that I took the exact analytical solution that is obtained for the point-like nucleus, which I am labeling here with the letter of B. Then you can ask, but the nucleus is not point-like Rastислava. Yes, I do agree. And the further step was just to include the finite nuclear size. In this way, like you take the potential of a homogeneous sphere with a radius of r, and then simply just calculate the electron wave functions which constitute these Fermi functions. But this is still not enough, because we know that the beta decay, even single or double beta decay, they do not decay as bare naked nuclei, but simply they are covered by the atomic electrons. So the final calculation was done by taking the advantage of the package radio and the solution of the major solution to the Thomas Fermi equation by finite nuclear size, but plus atomic screening. What does it mean? Atomic screening is nothing else that it simply just takes into account that when the electron is emitted and goes practically to infinity, it doesn't seize the daughter nucleus, but it sees the daughter nucleus shielded by the Z-1 electrons. So that means that actually the one that is going away is the one that is breaking this, making this nucleus as a neutral atom. And for that purpose, major Arnold solution to this Thomas Fermi equation was adopted. Just simply think of the Thomas Fermi function here defined as the effective charge that electron sees. So that means that there are two boundary conditions for this equation. Simply the first one, when electron is at origin or in the vicinity of the nucleus, there is no squaring at all. That's mean that why this is unity. And when it goes to infinity, it's 1 over Z simply. 1 stands for the beta decay. And this sometimes was made in one paper, a mistake in double beta decay. Authors forget to change it to 2. Once you have all these solutions, numerical solutions in your hand, you may start to construct the Fermi functions that enter the single beta decay spectrum, which are defined as the ratios of electron wave functions, the Dirac equations. So that means this is the relativistic calculation. And now I'm dividing these electron wave functions by the squares of spherical Bessel functions. This is simply just a fashionable way how to use and express the spectrum. Simply, it's very nice to have this feature that in the limit, when you will switch off the Coulomb interaction, you can forget about Thomas Fermi equation potential, then these Fermi functions will relax and go to unity. That means like the electron is propagating as a free particle. And as far as you might see on the left side and the right picture, the left panel, that's the Fermi function as it deviates slightly and is rescaled by switching off slightly these effects, starting from the A as the approximation, going to D, the best solution, which I would call. And also the right panel is for the P wave. So this was the situation that needed to be analyzed because in the beginning, I didn't know what will happen, what will change the spectrum by the endpoint. Now from this picture, it is evident that the spectrum will not change. The only thing is that the nuclear matrix elements that we will be eventually calculating needs to be rescaled. Okay, so that's the situation for the radium beta decay, which I'm quoting as the first unique forbidden beta decay. Then in principle, as I said in the beginning, we had the definition from Franz Devil Curie, how should the Curie function look like? Now what I'm doing and what I'm stating here is that for the first unique forbidden beta decay, in general not for radium, you should take a different definition of the Curie function, simply just to take the spectrum and then divide it by the momentum and electron energy and by the highest possible contribution from the partial waves of the electron. That means in our case, in the first unique forbidden beta decay, this is the P wave. Simply, why am I doing is that in this factor that is given in the blue circle is the same formula as you would have in the case of a low transition. But on the other hand, everything that is originating from the, let's call, forbiddenness of the beta decay is hidden in the square root of additional factor. And that means simply that if we will go close to the endpoint, the most advantageous thing how to use these Curie functions, not only for first unique forbidden beta decay, but also what I have done, and it is shown in this paper for arbitrary unique decay, you will always obtain that this S factor is going close to the endpoint, the unity. And that's very beautiful, that's very nice, because in principle, you may take any arbitrary nucleus, doesn't matter how high it is forbidden. The endpoint will be always governed by the same shape as in the case of the allowed transition. And in principle, then you can use the standard Curie function for the allowed transition. So this is the results of the studies of the forbidden beta decays. It was just like prolongation of these studies on the tritium decay, which is allowed one. So in this step, I would like to abandon the neutrino mass measurements, the tritium and rhenium single beta decays. And I would like to please hold your questions a little bit later on till we will end up with the double beta decay section. Now, actually, what I will use, I will just simply take the advantage of the development of the code and the numerical solutions to the Dirac equations. And simply in the studies of double beta decay, I will be not referring to them. I will be just simply using them in the phase-space factors that I will be presenting you. So as far as in the single beta decay, I need to present a few slides on the introduction to the double beta decay and their connection and the connection of this nuclear beta decay to neutrinos. So simply, double beta decay was proposed and also in the beginning of the 20th century by Maria Guppert-Meyer, who firstly calculated the nuclear matter, the half-life for the 2-neutrino double beta decay, which is a process that is allowed in the standard model. It is a mode which I will be discussing mostly in my talk, but it is the mode when the atomic nucleus decays by 2 neutrons change to 2 protons by 2 units. And therefore, 2 electrons and respectively 2 electroneutrinos are emitted. This is possible due to the pairing interaction in nuclei. So that means that the Z odd nucleus, which is neighbor of the even nucleus, is has a different mass, is lighter than this one, and the nucleus cannot then decay into the one, but it needs to decay only to the other neighbor. This is the common 2-neutrino double beta decay, the mode that would be actually allowed in the standard model. Why I'm proposing this, highlighting this, emphasizing is that not that later on, only 2 years, it was a proposal by Fury that in principle, there might exist a neutrino-less double beta decay, which is violating the lepton number conservation. And this process is just simply, from experimental point of view, that the nucleus changes, but emits only 2 electrons and no neutrinos. This process has not been observed yet, and it requires neutrino to be major nanoparticles and have some non-zero mass. From the experimental point of view, these 2 modes would distinguish, if I would just schematically plot the sum of the 2 emitted electrons in this way, that as in the single beta decay, for the sum of the 2 electrons in 2 neutrino beta decay, you would have a continuous spectrum going till the p-value of the process, while in the case of the 0 neutrino-less double beta decay, then you would expect only peak and events by the endpoint. And this question, whether these neutrinos are their own antiparticles, whether they are major nanoparticles or not, this is still open question until recent days. What I would like to just show you on this slide is simply just the formula that is associating the potentially observed half-life of the neutrino-less double beta decay, the effective Majorana mass, and the matrix element and the phase-space factor, which is something similar that was shown in single beta decays, but I'm not going to express and expand these quantities into details. Simply what I would like to just emphasize here is that in order to extract from possible experimental observation of a half-life, to extract the neutrino mass, you need to know precisely also the phase-space factors and also the nuclear matrix elements. And here I put in front of these products the axial vector constant, which I will be discussing later on, and that will be the issue of my talk as well. Just picture here is for the normal or inverted hierarchy of neutrinos, is just simply for the teaching purposes because I'm expanding the effective neutrino mass. So one can ask what is M1, M2, M3. I'm not going to use it and debate it. Well, let's turn our attention to the fact that, as I said, double beta decay, or even in the single beta decay, is not a decay of single neutron or 2 neutrons into 2 protons. It is a process that takes place in the nucleus. Now, that means, what does it mean? That in principle, if we would be simply calculating neutron decay into a proton or something like a neutron capture of neutrinos, we will be using the so-called like the bare values for the vector and axial constants, which are from the conservation of vector current. This one is firmly established that it's unity. The axial vector constant is established from the other measurements or from the particle data group, the value like 1.26, which is usually I'm using in calculations. But this is not true for the nuclei. That means that the extension to nuclei is not that trivial, as we can be treating those nucleons as free particles. That just simply tells us that we need to be actually paying attention what is the value of the axial vector constant in following what I will be explaining you. As far as I said, once you have on the left side of the equation is just the experimentally observed value of the half-life. You have phase space factors, matrix element, but if you will start playing with the unknown parameter, this is a little bit dangerous for the 2 neutrino, but for the neutrino double beta decay, because then you have an additional parameter that is tunable and interfering with the neutrino mass estimation. So just to give you the hint of that actually understanding, we would be interested, of course, in the neutrinos double beta decay, because that is the most prestigious mode of the double beta decay. However, one needs to understand very firmly what is the 2 neutrino double beta decay, the process, including and paying attention also to nuclear matrix elements, which are of crucial importance. And then you can only reliably calculate also matrix element for the neutrinos double beta decay. So in principle, what is the connection, or what is the idea behind this, is that both either the 2 neutrino or 0 neutrino as double beta decay operators connect the same states because it's one and the same nucleus. So further, I will just move on with what were the possibilities how to actually avoid some nuclear structure issues and problems. That was done by my mentor Feder a long time ago, actually 20 years ago. And it was like when he was proposing that we should be looking at not only at the half-life, but also on the energy distributions of emitted leptons. That means like once you have approximation, the so-called that was done proposed by Abad, like single state dominance, or the one that was paraphrased by Feder, higher state dominance. In principle, you might be able to extract the nuclear matrix element in front of the differential decay rates, and then simply just the normalized spectrum to unity or to the full decay rate is free of these uncertainties. That is very helpful. Of course, in the mixed state, in some mixed situation, whether you are not assuming only single state dominance or only higher state dominance, you cannot do anything. That's the most disadvantageous case. What I would like to just emphasize and put something a little bit here, theory from the single state dominance, that this is something like here given in equation what was shown in the previous picture. Like instead of taking the whole sum of the nuclear states of the intermediate nucleus, you're just simply taking either the first one, or then simply if you take just higher state dominance, you can drop out from this sum the higher state dominance as a sum, and simply approximate the energy denominator, the lepton energy in the denominators by some half-life, by some 1/2 of the Q value of the process. Simply, this is very good for the higher state dominance. As we have shown in previous studies, this approximation for the single state dominance is not really good one, but this was like the common approximation. As I said, the advantage of this approach, SSD or higher state dominance, is that the prediction for the half-life does not depend on the quenching. Simply, how you can understand is that the GA is a factor that will come out of the equation, and it will appear in the numerator and denominator and cancel out. Now, but let's go back. Where does this quenching will start playing more important role? So firstly, I quoted it several times on previous slides. I would just simply put this simple equation that what does it mean? Quenching is nothing else that you take just the value of the axial vector current for the free nucleon and reduce it by some Q factor, simply a number. And then you will obtain some effective value, which you will be using in your calculations. Well, from this, as I said in previous slides, CVC hypothesis, there's nothing wrong with the vector constant. What about the axial one? Is not that clear. At the quark level, we may say asymptotically free is everything, and then you may plug it as number one. Free for the nuclear level, let's say you can use it for tritium or neutron decay. That's okay. But what about the nuclei? So this is the problem. Now, people would like to treat this in several ways. I'm not going to discuss the details of how people quench and how do they calculation. Simply just one thing is just mentioning here that in principle they might be using also charge exchange reaction to extract the matrix element and obtain a value on this effective axial vector constant. That means the quenching coefficient. But what I would like to, rather than to be telling what other people do, is simply just to present our novel approach, I would call it. And that is simply just improving the description of, firstly, the 2 neutrino double beta decay rate, but then, as I said and stated in previous slides, it can be used and adopted for the 0 neutrinos double beta decay. Simply, the genuine idea looks like this. You take exactly the lepton energies in the energy denominators, realize that these values are in boundaries from -1/2 to +1/2 cube, and simply divide it by the combination of the masses of the initial and final nucleus and intermediate nucleus. Then what you do is simply you just perform a Taylor expansion of this quantity. So simply you will just extract take the differential decay rate that we hardly calculate in exact way, and then you are doing this expansion. That expansion eventually leads that the expression for the inverse of the half-life can be expanded. It can be expanded in this way. I'm showing you just the formula for the first 2 terms. That's the 0th order of this expansion epsilon, and that's the first one. That what you have is simply the 2 matrix elements, which you can actually, one you can always pick up out of the brackets, and you will end up with the ratio of these 2 matrix elements. And what you are remaining here in the brackets are simply just the phase space factors, which are calculated by means of those Fermi functions that I was presenting in the previous part of the talk. So in this way, you may, in principle, from the known half-life measured, extract the value of these effective axial constants. So this is the main part. Instead of just simply having a look on the 0 neutrinos double beta decay and extracting neutrinos, now you revert the issue and the query. You just simply take the known half-life, calculate theoretically these phase space factors by the means of that electron radial Fermi functions, the ratio and the matrix element by means of some nuclear structure model, and then what you will end up is the value of this effective axial constant. And as far as our theory calculations were actually provided to commons and collaborations, so we have a common paper on that, which is quoted here. Now, as I said in the previous slide, the expansion was made up to the 2nd order of that expansion. But one can ask, and what about the rest? We can go up to the infinity. Yes, that's right. And here would I like to expand this half-life up to the 4th order and expand the phase space factors and the contribution to the decay rates in more details. But just to show you what can be done numerically, it will be much more clear, I suppose. That in principle, as you have here, I didn't quote it here. Here I used just the label J. As you're going to higher and higher order with these integer, you go to higher values. And these are the values that are quoted here, I'm sorry, but with the letter N. So that means simply just that the standard common spectrum with no expansion would be this one with n equals 0, which resembles for the double beta decay people. How does it look like the common spectrum of single electron energy distribution and the sum of the two electron energies? And then, as you can see, these higher contributions, n equals 2 and 4, they have different behavior. So the shape is a little bit different and more deviates in the case of the single electron energy spectrum, while in the sum electron energy spectrum, it's a little bit approximately the same. But these spectra in the left side of the slide are normalized to unity. Eventually, what you should be interested in is the normalization to the full decay rate. So, and that is actually shown here on this right picture, simply as you can see as the order of that contribution increases. The overall contribution, as you might see, decreases, which is actually very nice and expected. That means simply as you will be taking higher and higher orders, you are taking just a smaller and smaller corrections, which is quite good, because then it means this justifies our approximation if you will take up to the order of 2, which was used by the Kahneman analysis. So indeed, in case these studies are similar like the ones that I presented in previous and were done by Feder a few years ago by the single state domains, again, the experimentalists and also the theoreticians need to think of not only on the half-life, like the full decay rate, but also on the differential decay rates and distributions. What we were also thinking of in connection with this quenching issue is also not only to exploit the double beta decay, the 2 neutrino mode, but also the muon capture rates on the nuclei, which are double beta decay, but also taking into the intermediate state of the nucleus. And we performed the calculation and found out, actually, a very recent paper, that in principle, in the muon capture rates, unlike some other authors, we do not need some very strong quenching in our calculations to have some good results with commonly known Fuji-Primakov calculations of the decay rates. So only soft quenching is needed. I apologize for that. I didn't put there the effective value of the DCF is used here, 0.8. So this is the idea that is still ongoing. And this year we have another paper which is going to be, I didn't succeed to present another experimental observable, which are angular distributions. As far I was showing you the electron energy distribution, single ones, and the sum of the electron distributions. But there is also in some experiments like the Nemo-free super Nemo that allows to measure the angle of the outgoing electrons, but I will be mentioning this in some subsequent talks as a laboratory. Simply, I would just stop here with these theoretical studies, which I would like to just say that we, together with our colleagues, we were awarded by the joint JINR prizes for the year 2020. And this is just something like only the highlight of those work that is presented there, which I was trying to pick up only my contribution in the field of that. So, and then by this, I will be just simply going to the experimental part. But as I said to Evgeny Alexandrovich, that if there are some questions here, I'm open for some debate till we move on to some other topic.
Okay, let's see if there is any questions. Okay, please raise your hands. So I see no hands, but I have one question about the rhenium decay.
The rhenium decay.
Come back to I think 12 or 13. Yes.
Rhenium decay. You mean the spectrum you would like to see?
Yeah. Yes. Maybe this one or next one. Oh, this one is okay. As you know, the rhenium is main part of the energy is coming not from nuclear but from atomic changes, because for binding energy for atomic shell is much higher than this decay energy. So I think even for K shell, for rhenium to osmium is about 2 keV for K shell for each electron changes. And well, this means that this decay cannot happen for rhenium nuclei if there is no electrons in the shells. So just energy will be not enough.
I'm sorry, once more.
How this is taken into account in the theory?
No, Evgeny Alexandrovich, perhaps you are thinking of something different. Well, just let me briefly just comment. I presented only results that were already published. And you are right, the atomic effects are crucial in rhenium beta decay, but these are the ongoing things which I don't want to present because otherwise my mentor would not be very happy with that. But firstly, what I would like to stress and highlight why I put this radiant decay here is that there is a very recent paper by the Klaus Blom and his company by the spanning terms who remeasured the Q value. But this is the ground state to ground state transition. That means that you have initial nucleus is in the ground state, then the final nucleus is in the ground state. But the atomic effects are important, but I don't think so that you can observe the decay only if you will strip off the electrons, if this is the idea. But perhaps I didn't get it. Can you repeat your questions one more?
Well, what I said that when you change from rhenium to osmium,
yes.
So for K shell electrons, changes in binding energy is about 2 keV. So for each electron. So it means that if you consider all changes of the atomic shells, if you calculate the total sum of these energies, you will get about, I think, 10 keV. This means that if you have naked rhenium nuclei, it will not decay to osmium. And this that means that with your calculation, you have to consider not nuclei but atom as well.
Yes.
And then actually I didn't finish my question. So at once you have the atom and all these atomic transitions. This transition are very fast. Then you have natural width of the atomic transitions, and then shape of your decay actually will be affected by this natural width. Is it taken into account in consideration?
Well, yeah. Well, the point was that the Murray experiment, they were treating and they were taking the advantage of the bolometric method. So that's why these effects were somehow naturally taken into account. No matter what will happen with this final atom, it will de-excite and it will be eventually turned into a heat. At least that was the idea.
Okay, maybe we can discuss later. So
okay, perhaps we can discuss. Yes. But what are actually maybe we cannot discuss because, as I said, this is just recent ongoing work that we started this year, and I would like to just finish to publish the paper and then open it publicly. But privately, of course, we can discuss about the intermediate results. Okay, I'm sorry, not openly. I will be not speaking.
Okay, any other question about this part? I see no question, so let's continue to experimental part of your talk.
Okay, so I will just move to that slide. Okay, which one? That was like, that's like in double beta decay, 2 parts of Rastислava here are also that I'm also involved in the experiment of Baikal GVD neutrino telescope, and I would like to present also this experiment here. In the beginning, I show you this picture in the introduction, stating that I will be speaking of low energy neutrinos, let's say MeV scale. What I will be just right now presenting you are the few slides for the Baikal GVD neutrino telescope, which aims at completely different neutrinos. That means very high energy scale, galactic or extragalactic energies. I know that this talk for our laboratory may be a little bit redundant, but I need to put this slide, the introductory slide. What is Baikal GVD neutrino telescope? As far as I think everybody knows, but it's a 3-dimensional array which is still under construction, and we hope that we will finish and conclude the phase with 1 cubic kilometer scale of photosensors that are merged in Lake Baikal. If you know, here is something like on the map is Irkutsk. So this is the location, southern western basin of Lake Baikal was chosen due to the fact that if you're going only 3.6 kilometers from the shore, you will really hit the flat lake bed. And that is very advantageous for the experimental because all the parts of the telescopes are at the same level. the physics goes, and the aim of the telescopes are the investigation, as I said in the previous slide, the galactic and extragalactic neutrino point sources, and in general to measure the neutrino flux. In principle, it is suitable for some dark matter and exotic particle searches. And as now in the last years, very fashionable start this tool for multi-messenger astronomy, which is very now promoted by the discovery of the gravitational waves and joint analysis alert systems. So simply just briefly give you an idea, the Baikal-GVD neutrino telescopes consist at recent stage of 2,304 optical modules. Optical modules, the basic detection unit that is assembled in our laboratory in Dubna, are spherical glasses which holds the photomultipliers. A photomultiplier simply just registers the Cherenkov light from the relativistic particles. And the structure of the detector is goes like this. 12 optical modules attached to the string are simply joined and attached to the section control module. And this is the upper unit of the telescope, which is called section. So this optical module as the basic detection unit is unified in section. Each section has its own electronics. And then on that string, you have 3 sections simply. It's 3 sections, one above the other. The distance between each optical module on this string is 15 meters. That's the vertical distance. If you have 8 strings, 1 is central one and 7 peripheral one, this unit we called Baikal-GVD cluster. So that the cluster is just simply fully independent detection unit, which is connected to the shore by the cable, independent cable from the other clusters. Just to have an idea, the height is 525 meters and the diameter is 120 meters. So in principle, the upper optical module, which I will be using, and this is important to mention, is installed at the depth of 750 meters. And the bottom one, 1,275 meters. The depth of the lake in this place is 1,366 meters. It makes sense not to install optically sensitive device by the bottom because there's something like a mud and floats there. Then the optical body properties are not that ideal. Now, what I need to mention is that the cluster data acquisition system uses the trigger that we use, and this is simply just that 2 neighboring optical modules on a given section will just need to give a signal more than 1.5 photoelectrons and the other one more than 4 photoelectrons in a time window less than 100 nanoseconds. And simply just the cluster is, let's say, capable of the maximum trigger rate about 200 hertz. Usually it's about 40 to 60. Okay, I will be not going really into the details, but as far as you might understand, having this detector out there in the wild nature, there is a time called winter expedition when you need to come there and do some technical work there, even ourselves, people sitting behind the computers. So that's me pulling just those ice on the lake there. This is the cold winter expedition, which is needed for the expansion of the detector. Simply during the 2 weeks, during the 2 months where there is the frozen ice on the lake, we have there our lagger instruments and technical things there, and doing either the reparation of some broken parts or installing and enlarging the telescope. As far as the aim is to have as high volume as possible. Simply, the neutrinos doesn't like to interact very often. That's the problem. The picture of this winter expedition 2021 is that there are 8 clusters already deployed. Beside them, there are 3 laser stations and 2 experimental strings, which I'm not going to talk about. It's just too technical, and other people should be giving talk on this. Simply, just the situation here is given as a deployment schedule would move on that each subsequent winter expedition, we hope to build 2 more clusters every year. Now, to the particular task that I'm working on is that the Baikal Lake itself is the source of the light. Here is just a picture, a sketch of the muon passing through one cluster of the Baikal GVD Neutrino telescope. Now that executed a trigger. That means that every particular optical module, 288 of them on a given cluster, are registering a time window of 5 microseconds. That means that every impulse, every particular photon that has entered and given a signal onto optical module will be recorded. And this is very good for this is good for other studies than just to be for the neutrino detection. So that means once you have a muon that is passing, triggers the whole system. But then what you actually continuously observing is the background light of the, which I call Baikal ambient light field. Light field, why is it field? I will explain a little bit later. Simply just think of that. It is the impulse that was detected on optical module. And we surely know that it is an impulse that may not give you a trigger. That's the data analysis is made in that way that the trigger pulses are placed here in the middle of the 5 microsecond windows. Here from this sketch of this picture on the left side, you may see that these big bubbles corresponds to higher charges on the optical modules detected. And these soul guys, as you might see here and there, that's exactly the noise of the lake. That is input for my studies. And from the amount of these registered background light, actually, which is derived from the photomultiplicative noise rates from each and particular optical module in the cluster. So one may ask, and okay, Rastислava, and what are the properties of this Baikal light field? So the very general picture that I have seen since 2015 and repeated almost every year is as following. In the beginning of the year, that means when the ice melts and there is nothing there, it's simply just a flat background. And this is just a very good situation for the Monte Carlo people because they can take the background conditions uniform, which is good for calculations. On the other hand, what happens there during the summertime is that there is an increase of this photomultiplier noise rates, and the light field actually increases activity. That means, indeed, the lake shines a little bit more. And then by the end of the year, what you see is that there are some cold period, that is a period of calm deviations of the noise rates going up and down, up and down. So this is just the simply typical picture which I have seen there for almost 6 years. It's except 1 year, which I will be not discussing here. And the picture is like that there are relatively 2 stable plateaus, and they are intermitted by highly luminescent water. But where the luminescence, I will come back a little bit later. Right now, I believe just speaking of the noise rates and or the light field. Now, once, you know, how does it look like? What's the time dependence of this Baikal light? You may ask, and what is the charge distribution of this light? And this is actually the answer to this question is given here in the right panel. So what I did is that I pick up the period, the stable period. It's one from the beginning of the year. And the active period, really, when you can see these needles here in the picture, and simply plot the charge distributions of the pulses. And as far as you may see, they remain almost and practically the same. In other words, it doesn't matter whether you have high activity in Lake Baikal of this light field or low one, it's still the majority, its emission, the majority of the light field is emitted in single photoelectron peaks. That means here is the 1, here's the 5 photoelectrons, here's the 1. So this is where the Gaussian, really, what we are using for the charge calibration conversion sits in. So this is how the looks like picture. These, of course, this tail I will not be discussing because we will be studying this later on, which I assume that these are the so-called after pulses, predominantly made by the single photoelectron contribution. Well, and how does it look like if, for instance, the discrimination level would be set to 1 photoelectrons? Simply just this picture will be like the noise rates will decrease by half. That means nothing particularly interesting is going on there in the case of the charge distributions. That practically means each pulse that is detected by our optical module in these studies is equal to each photon. Now, as I said, the general feature repeated for years since 2015, 16, and so on. I'm just plotting not here the whole period of here, but only the merging picture of the 3 years, 18, 19, and 20. As far as you might see, that there is actually a typical situation here, beginning of the year, oh, it goes there. Here, the interruption, that's our winter expedition where we switch off the telescope, particular one, the data were not taken by the cluster. And then again, another year, a highly luminescent activity, and another. And then another one, and another one. And to this one, I will be speaking of a little bit later on. But just simply just to give you a little bit different picture, is that here I'm plotting the activity and the registered pulses for different optical modules representing different depths. But this picture is a little bit better to understand what is going on there in the late Baikal. So simply, here is the numeration of optical modules, which is equivalent to the depth. Thinking of that, like 36 is the top optical module, the 0 is the low one. And then what you have is just, instead of the time, we use the run simply ID. And the color tells you by the how many impulses were detected. Here the scale, so the red one goes something like the 200 kilohertz, corresponds to this one. And that means, and the blue ones are the ones that hits the stable plateau of the electronic background of the optical module indeed. So what you might see from this picture is evident. Now, as the time goes by within the year, you see that something is approaching the top of the cluster, and then it's slowly moving down. And this is the situation that might be visible even here in this picture, but here I think this is much better for the representations. And not only that, from this picture you might see that you might actually find out the slope of this movement, but you can also understand that the amplitude of that how else call it, by just luminescent layer of that cloud, activity of that cloud decreases with time also, or with the depth. As far as you may see, here is the red one, 200 kilohertz, and then it goes here barely to something like 120 and so on. So from, as I said, from the analysis, which is given here, but you may use also the fitting procedures and so on, you may estimate what are the things that are going on there. And firstly, by this, you can estimate the velocity of this cloud that is moving downwards. As you might see, the maximum is 16 meters per day in August. 16 meters, I recall you, 15 meters is the distance between two optical modules. And just simply, just to give you an idea, well, usually in environmental studies that I have found out, the sedimentation goes something like millimeters per day. So these are sometimes astonishing numbers, what is going on. And of course, the other table is showing us what is the peak noise rates evolution with date. That means that the amplitude is decreasing when you might see the torrent changes appear in the summertime. Okay, so these were the pictures that you should have in mind that I had in my head in 2016 when I look at the data from 15 and 2019. But then what I would like to also just tell you that there's, as I said, the light field. Why light field, colleague? Because it doesn't only changes with the time, but also with the spatial variables. And then I constructed during the calm period the depth profile of these decrease of the luminescent activity or this cloud activity, as we might say then. And simply, it remains the same within the 3 years. And it is the same also, I didn't just quote it here, the year 2016, which was in the previous studies. And it looks like there is a really exponential decrease of the activity with the depth. Instead of this tail here, which I'm not fitting because that's, as far as I said, the depth is 1,366 meters. So there's something like, what I'm thinking of is the effect of torrent flows, just it's picking up some mud and dust from the wet lake, and then the water is not that clean, and that's like here. Okay, and what I would like to actually highlight and brought your attention to is that I presented this summer at the ICRC conference is this tail. And this is something that we haven't observed so far. So it's a unique event that this highly luminescent layer, no matter what is the reason for just emission of the light there, that was moving upwards. So that means as I was looking and fitting the data there, which is much more visible in this right picture, is that you might see that in the beginning of the year, it started to fall down. It looked exactly as the typical year, but then it moved upwards almost to the top of that cluster, which remains a mystery to me. As far as you might see, this is the year 2021. And I'm very eager to finish this year the data analysis and start thinking of that on a different cluster. What is happening there? If this uprise is proposed with something like this in neighboring clusters, or whatsoever is going on there, and the estimated speed even reached the maximum value. So my findings on the previous values from 2016 were overseen by this speed, 28 meters per day, which is very, very, very high. And simply from that picture of increase this activity, there are also some other effects. Well, by the calm period, what we are observing there are something like, as I call it, calm waves. That means like these are something like on a given particular optical module, waves of this activity going up and down, going up and down. So this is still also work in progress, which I would like to fit by the neighboring clusters, just to see not only that it rises and falls down, but on the neighboring cluster optical module, what is the situation like. And during the active period, I need to stress also that there are some remarkable things going on where you have the increase of the activity and then it just simply drops down by 150 kilohertz, which is drastically big change. And that makes also a big head to us in Monte Carlo simulations, because once you would like to fit and approximate this, it's not a value for the noise rates of the given optical module, and then it simply just drops down. Turns out that we need to abandon the run and we need to go to something like small time windows. This one, all these studies, I didn't mention that, but each point is 5 minutes of the record of the telescope data here. So these preliminary results I have already shown in previous conferences and published. And also, as I said, this is like the work in progress of still under debate. And but then what I would like to also say, because I would like to apologize that my contribution is not a very good one. Last weekend, I spent also promoting Baikal GVD Neutrino telescope at a public place, Saturday and Sunday at VDNH in Moscow. And just simply from my point of view, I would say that people are really interested in what's going on in Lake Baikal. And the first question immediately that I obtained there was, are you not hurting Baikal? Is it safe for Baikal? And even these studies that I showed you are actually a good confirmation that the Baikal GVD Neutrino telescope is not only observing neutrinos, which is aimed for, but also the cleanness of the water of Lake Baikal. So that's the answer I was just giving. Like, indeed, you may use it as a tool for fundamental studies, just for some application and some practical purposes as well. And these points, I would just simply pick up those 3 particular tasks that I pick up during this talk. Those were just direct neutrino mass measurements, exploiting the tritium and the rhenium decay in general as the load, and unique forbidden beta decays. And the issue of the quenching that was addressed in the double beta decay, and finally, eventually also the light field studies the luminescence of Baikal water, naming time and spatial variations of the flows. And I would say that at this point, I would conclude my talk, and I'm open for further questions.
Okay, thank you, Rastislav. Okay, for really interesting talk. So let's see if there are any questions. Okay, please raise your hands if you want to ask something. Okay, let me ask you one question. Okay. So about the second part, so you said there is this high rate of this noise or background events, noise events, but is it caused any background for physics in Baikal?
Yes, of course. Well, I mean, of course, let me go to that picture in the input data. Well, this is the typical picture that we might have seen. And of course, this noise of the Baikal light field is usually given as a cut. Firstly, we say that everything that come earlier than there was a trigger was for sure noise. But the noise also is distributed here in this rest of the time. We know that colleagues use for the data analysis, mean reconstruction and cascades. And yes, the answer is yes. Of course, the noise is present also in the studies and the reconstructions of the neutrino events. And it makes a problem, of course.
But is it affect only, let's say, accuracy of reconstruction, or it may produce fake events?
Fake events, not really, not fake event, because the Baikal GVD is aimed for high energies. And as I said, in this charge distribution, noise will just give you perhaps 1 to 1.5 photoelectrons, not more. While in the cascades or in MEOs, people are aiming at least at few photon electrons, particular optical module. So that means not really. It cannot produce like really the fake neutrino event in the detector. It only worsens energy distribution cascade or position that people are using in estimation and so on.
Okay, thank you. So I see that Anwar Inayata want to ask a question.
I have some remark. The rhenium is no longer relevant as an object of calorimetric measurements of the neutrino mass in the Mars experiment. For these problems, holmium is more acceptable, yes?
Yes, yes. That's the echo experiment and other ones, yes. But what surprised me, actually, I'm sorry for that. That was a horrible weather time in Moscow, and I was practically speaking the whole time and answering the questions. Let me go back to this one. I put here the slides on uranium, and actually why we started to investigate it once again is that there appeared this very recent measurement by the group. So I think me and my advisor Fedor, that in principle, as Evgeny Alexandrovich stated, we didn't finish the theoretical investigation really indeed, because, okay, it will not be Mary experiment, it might be a different name, but people are also interested in these measurements of this rhenium beta decay, and we are just waiting for that. Simply, once what we can offer, as in those days, we were offering them the accurate theoretical description, the best one as possible at the time. Now what we would like to do is exactly as Evgeny said, take the atomic effects really accurately into account. That means that what we are right now doing, we are studying theoretically the atomic effects exchange corrections. So, sorry for that I need to say that openly, but this is still ongoing work. We didn't finish.
Thank you.
Yeah, but yeah, for ECHO, yeah, I was actually also trying perhaps to get involved into this ECHO collaboration, but then I decided like there are some other interests, and I picked up Baikal GVD.
Thank you.
Okay, thank you. So any other questions? So I see no questions. So let's say thanks to Rastislav again. Thank you a lot, and everyone have a nice day.
Okay. And of course, people from RH, we can discuss privately with this by the Blackboard. Okay.
Thank you.